For decades, offshore rig workers lucky enough to survive have told stories of terrifying walls of water appearing out of nowhere in the middle of the ocean. They described waves with almost vertical faces, preceded by a deep trough. These waves shattered control room windows, buckled massive steel support pillars, and threatened to tear entire oil platforms from their moorings and drag them to the bottom. However, 20th century oceanographers and mathematicians treated these stories with heavy skepticism. According to classical wave models, the ocean is a predictable system. Calculations showed that a wave over 20 meters, 65 feet, high could only form once every 10,000 years. Therefore, reports of 25-meter monsters were dismissed as optical illusions caused by fear and heavy pitching during a storm. That is, until New Year's Day in the North Sea. The Draupner E Platform wasn't a classic oil rig. It was a crucial support node for a gas pipeline owned by the Norwegian company Statoil, located about 160 kilometers, 100 miles, off the coast of Norway. It stood on steel jacket legs, firmly secured to the sea floor. The platform's lower deck sat about 20 meters above the average sea level. Engineers had designed it with a massive safety margin, expecting it to withstand extreme storms. But the most important detail for our story was a laser sensor. A highly accurate laser rangefinder was installed on the platform, pointing straight down. Its sole job was to continuously measure the distance to the water's surface. The new year began with a brutal hurricane-force storm. Wind speeds over the North Sea reached 40 to 45 knots. The ocean had turned into a chaotic mess of foam and water. Sensors indicated that the significant wave height, the average height of the highest one-third of waves at any given moment, was about 11 to 12 meters. This was a very powerful storm, but perfectly normal for the North Sea in winter. Due to the danger, the platform manager ordered all workers to stop any exterior tasks and remain inside the interior modules. At 3:20 p.m. local time, the platform suddenly shuddered from a colossal impact. The vibration traveled through all the steel structures. It didn't feel like the rhythmic pounding of regular storm waves. It felt as if a freight train had slammed into the platform from below. Because everyone was safely inside, no one was injured. When the storm subsided slightly, engineers went outside and found a strange scene. Equipment and walkways that had been securely fastened to the lower deck, more than 20 meters above the water, were bent or torn away. The water simply shouldn't have reached that high. The real shock came when engineers downloaded the data from the laser sensor. The graph showed the steady rhythm of 10 to 12 meter waves until suddenly, at 3:20 p.m., the line skyrocketed. The sensor had recorded a single wave with the following parameters. Maximum height from trough to crest, 25.6 meters, 84 feet. Crest elevation above zero sea level, 18.5 meters, 61 feet. At first, company scientists assumed the laser had malfunctioned. Perhaps a bird had flown past, or the beam had bounced off thick sea foam. The data was sent to the Norwegian Geotechnical Institute for an independent review. After months of rigorous analysis of the laser's technical condition and telemetry data, the verdict was clear. The instrument was working perfectly. There was no error. The Draupner platform had indeed been struck by an 8-story wall of water. This event forced the scientific community to rewrite textbooks. The Draupner wave proved that the ocean operates according to non-linear laws. A rogue wave is not a tsunami, which is caused by underwater earthquakes. It is born right in the open sea through a process called constructive interference. While the math is complex, the basic idea is straightforward. Different groups of waves, moving at different speeds and in different directions, randomly meet in one spot. Instead of just passing through one another, the faster waves essentially catch up to the slower ones, absorb their kinetic energy, and merge into one giant, highly unstable peak of water. This monster exists for only a few minutes, travels a couple of kilometers, and then collapses. But if a vessel or platform is in its path, the consequences are catastrophic. The Draupner wave solved the mystery of dozens of large ships that had vanished without a trace. A typical 12-meter storm wave exerts a pressure on a ship's hull of about 15 tons per square meter. Ships were designed to withstand pressures of around 20 to 30 tons per square meter. However, measurements showed that the steep, nearly vertical wall of a rogue wave exerts a pressure of 100 to an incredible 150 tons per square meter. It simply crushes a steel hull, leaving the crew no chance. Following 1995, the European Space Agency launched the Max Wave project, pointing satellite radars at the ocean's surfaces. In just their first 3 weeks of operation, they recorded more than 10 waves over 25 meters high worldwide. The myth turned out to be a daily reality of the open ocean. The Draupner wasn't the only offshore structure to face the ocean's wrath. Over the years, other platforms have encountered terrifying rogue waves. On December 30th, 2015, this semi-submersible drilling rig was operating in the troll field of the North Sea during a severe winter storm. A massive freak wave struck the rig, smashing right through the reinforced windows of the accommodation module. Tragically, this incident resulted in the death of 1 worker and injuries to 2 others, proving that even modern offshore habitats are vulnerable to these sudden, towering impacts. Workers on a neighboring vessel in the North Sea captured terrifying video footage of a colossal wave, estimated at roughly 80 feet, 24 meters high, slamming directly into the legs and splashing all the way up to the underside of the Dunbar oil platform. The visual evidence served as a chilling reminder of the raw power these structures endure. While operating off the coast of Newfoundland, this enormous semi-submersible rig sank during a fierce winter storm, resulting in the loss of all 84 crew members. While the exact chain of events remains debated, many marine experts suspect a massive rogue wave smashed through the rig's ballast control room window, short-circuiting the electrical panels and leading to fatal flooding and loss of stability. Today, the scientific focus has shifted from proving rogue waves exist to predicting exactly when and where they will strike. Oceanographers and tech researchers are now leveraging advanced artificial intelligence and massive datasets from global satellite radar networks to forecast these elusive giants. By feeding algorithms real-time telemetry on wind patterns, ocean depths, and intersecting wave groups, neural networks are learning to recognize the highly specific ocean states that give birth to monster waves. While we cannot stop the ocean from unleashing its chaotic energy, these predictive models aim to create an early warning system, giving ship captains and rig operators the precious few minutes they need to lock down equipment or alter course.